Unit 9 was our most recent 2 units before we started review. For us, this was units 9 and 10. So we split unit 9 into 2 units. This ties in delta G, this ties in delta S, and then it gets into electrochemistry. So then we tie in delta G to cell potential. So for Unit 9, we start Unit 9 talking about entropy. So topic 1 looks at entropy. Remember, entropy is delta S. College Board wants us to talk about entropy in terms of how matter or energy is dispersed in a system. We were using the term disorder, but College Board has actually said now they want us to use the term dispersed. So entropy is a measure of how dispersed the energy or the matter is within a system. If we think about what I mean by dispersed, we're talking about how spread out it is. So entropy increases when matter becomes more dispersed, when it's more free to move. So if it's easier for you to think about free to move, we can think about it that way. So some changes that result in a positive delta S. Positive delta S means higher entropy. Higher entropy, more free to move. If we increase the moles, right, we're increasing the moles of something, or we're increasing the moles within a system. Matter is more dispersed. There are more particles dispersed, free to move in the system. Increasing temperature increases entropy. They're moving faster, right? They're more dispersed. Increasing volume. So we have a small container, we increase the size of the volume. There's now more space for them to move. Solid to liquid to gas. So gas has the highest entropy. Solid has the least amount of entropy. And then if we form more complicated molecules. So forming more complicated molecules, if we have 1 mole of solid to 1 mole of solid, but we realize that the product is a more complicated molecule, that's increasing entropy. Now, if it helps for you to remember disorder, that's fine. But if it wants us to explain, wants us to talk about how dispersed the matter is, how spread out matter is. So we see questions about entropy, which of the following would have a positive or negative entropy? So we have to be able to use topic 1 to think about entropy in a qualitative way. So thinking about how entropy increases or decreases. Now topic 2 wants us to actually look at calculating entropy. This equation is on our equation sheet. This looks very similar to heat of formation. We're using absolute entropies to calculate the entropy change of a reaction. So remember that heat of formation of an element in its standard state is 0. Absolute entropy is not 0, because entropy is how dispersed matter is. Only a pure crystal at absolute 0 would have an entropy of 0, because everything else moves. O2 gas has motion. N2 gas has motion. It has entropy. So again, we're given absolute entropy values. You have to be given heats of formation or absolute entropy values. And what we do is the exact same as heat of formation. We sum up the products minus the sum of reactants, take into account coefficients. Now, when we're doing calculations, we always need to remember to pay attention to units because this is joules per mole. Entropy is given in joules per mole. Topic 3 looks at free energy and thermodynamic favorability. So free energy is delta G. Remember, the point of us calculating delta G is to tell whether or not a reaction is thermodynamically favorable. Is it spontaneous or not? They use the terms thermodynamically favorable to tell us that the reaction will happen or the reaction will not happen. The reason that they like using the term thermodynamically favorable is because that helps us to get out of our mind that spontaneous happens quickly. Thermodynamically favorable means the reaction happens on its own, but it might not be fast. Right? Rust happens on its own, but rust takes a really long time. A process is thermodynamically favorable when delta G is less than 0. So when delta G is negative, the reaction is thermodynamically favored. If delta G is positive, the reaction is not thermodynamically favored, but the reverse reaction would be favored. So in order to get the reaction to occur, in order to get the forward reaction to occur, we'd have to add energy. If delta G is 0, the process is at equilibrium. Remember, a phase change happens when delta G is 0. So neither the forward or the reverse process is favored. We would say it's at equilibrium. One way to calculate delta G is to use another familiar looking equation. We have this equation for delta H, delta S, and delta G. The sum of the free energy of formation of products minus the sum of the free energy of formation of reactants. Again, take into account coefficients, but you sum up all of the products minus the sum of all of the reactants. You would have to be given the free energy of formation in a table in order to calculate. So look at what you're given in the problem to figure out what you might have to use, because they'll always have to give you values to plug in. Now, going along with predicting favorability, still part of topic 3, we looked at this table. This table is actually given to you in the unit guide. So topic 3 is actually 2 pages. So if you actually flip over to the second part of topic 3, you're given this table. And so with this table, this is how we related delta G, delta H, and delta S. You need to know this table. Now, this equation is on your equation sheet. Delta G equals delta H minus T delta S is on your equation sheet. This helps us to determine at what conditions is a reaction favored. Well, in order for a reaction to be favored, delta G has to be negative. Remember, nature favors low energy and high entropy. Nature favors a negative delta H and a positive delta S. So since nature favors a negative delta H and a positive delta S, the reaction would be favored at all temperatures. Now, if we do the opposite of that, high energy and lots of order, a negative entropy. Well, if we do a high energy and a negative entropy, nature never wants that. That reaction would not be favored at any temperature. Now, be very, very careful when you are plugging in to solve for delta G. Please remember that entropy is joules per Kelvin. So when you are plugging in up here, delta H is kilojoules. Delta G is typically kilojoules. T would be Kelvin because of the unit. Delta S is joules per Kelvin. So you have to convert to kilojoules if you are doing calculations. Now, if delta H and delta S are the same sign, delta H and delta S are the same sign, then as temperature changes, favorability changes. When they're both positive, then you just have to think, okay, if they're both positive, as I increase temperature, what will eventually happen? Well, if they're both positive, remember this delta S is normally a really small number because we have to convert to kilojoules. So at a low temperature, this is going to be a really small number. So this will remain positive. So delta G will remain positive. So at low temperatures, it's not favored. But as we increase this higher and higher and higher and higher, eventually this T delta S value is going to be greater than delta H. So eventually delta G will become negative. So at high temperatures, that would be favored. And notice how if they're both negative, it's the opposite. So when delta H and delta S are the same sign, you have to figure out how does temperature affect favorability. But you have to remember that entropy has to be converted. Now, the biggest thing with topic 4, this looks at thermodynamic and kinetic control. So remember, thermodynamics tells us, is the reaction favorable? Will the reaction happen on its own? It does not tell us anything about kinetics. So there are a lot of processes that are favored, but we do not see them happening because they have such a slow rate. Again, rust is an example. Corrosion. Over time, they happen on their own. We don't see it occurring at a measurable rate. What that means is that these processes are under kinetic control. If you see an example, if you see a multiple choice question that delta G is negative, and it says, why doesn't this reaction happen? Why don't we see the reaction happening? Well, we see a negative delta G, that tells us, well, this reaction is favored. This reaction will happen on its own. But the reason the rate might be so slow is because of this, high activation energy. If a process has a high activation energy, even though the reaction is favored, it's going to be slow because the reactants need to overcome the high activation energy in order to form products. That is all that topic 4 covers. If a process is thermodynamically favored but is slow, it's due to a high activation energy. And topic 5 ties in free energy and equilibrium. So what does it mean for a reaction to be favored or not favored? If a reaction is thermodynamically favored, delta G is less than 0. We know that. Delta G is negative. K is greater than 1. In any thermodynamically favored process, equilibrium constant is greater than 1. Products are favored. Remember, when the equilibrium constant is greater than 1, products are favored. If your reaction is not thermodynamically favorable, delta G is positive. Well, if delta G is positive, it's not thermodynamically favored. That means it's not going to happen. So the reactants are going to be favored. K is less than 1. Remember, K cannot be negative. K cannot be negative. And so that means that we're thinking about K being some decimal. Delta G is near 0. K will be close to 1. And then the equation that relates delta G and K, the equilibrium constant, that's on your equation sheet. Delta G equals negative R times T times ln K. When you want to do anything with energy, you're going to use the energy R. You're going to use the one that has joules in it, 8.314. You can also solve for K. You divide by negative RT. You do E. So E to the negative delta G over RT equals K. That's another way you can solve. You rearrange that equation. And so this actually just, I wanted to kind of put everything on a slide. I know we haven't talked about cell potential yet, but this slide is useful because it helps you to see delta G and K as well as cell potential. So different ways that we calculate delta G. It is all based on what you're given in the problem. I could have also added negative RT ln K on here. So depending on what you have in the problem, depends on how you can calculate delta G. You have the equilibrium constant. Look on your equation sheet. See what equations you have on your equation sheet. Now, this came from Unit 7. I'm just going to talk very quickly on this. And the biggest thing is actually these 2 bullet points right here. This actually ties more into breaking and forming bonds. But topic 14 of Unit 7 talks about what happens when you dissolve a salt in water. So what happens to enthalpy what happens to entropy and what does that mean about free energy. So remember that breaking solute and solvent particles apart, so breaking anything apart, separating anything is always endothermic. Forming a solution is always exothermic. When you form a solution, you're actually increasing the entropy. So you're increasing the entropy when you create a solution. Now delta G, the free energy, is going to be based on what is your value of delta H, what is your value of delta S, and what temperature are you at. So the biggest thing with this is just keeping in mind that delta H is based on how much are you separating, how much are you putting together, and delta S depends on how much disorder or dispersal are you creating within the solution. Then topic 6, so this talks about coupled reactions, and this kind of segues us into electrochem. Coupled reactions is Hess's law. So you couple reactions when you put two reactions together, almost like a mechanism. When you have one reaction that is not thermodynamically favored, you can make it favored by combining it with another process, coupling the reaction. So essentially what topic 6 says is that you can use an external source of energy to make something work. Run electricity through it, an electrolytic cell, make a process happen. They use the example of light to make photosynthesis work. All right, you need energy in order for a process to work. So if something is thermodynamically unfavorable, you can make it favored by just adding energy. Right? Add energy to make it work. Now, the rest of Unit 9 ties into electrochemistry. So topic 7 is a very broad topic about galvanic or voltaic and electrolytic cells. And so what I did is I just put kind of a comparison of the two types of electrochemical cells up here and then what they both have in common. This came right out of your Unit 10 notes. So if you need to go back and refer to electrochemistry, just make yourself a note. It's Unit 10, your guys' Unit 10 notes. So a galvanic or voltaic cell, these terms are used interchangeably. Galvanic cell is thermodynamically favored. It happens on its own. You have the anode and the cathode in two separate compartments in half cells. You need a salt bridge. The purpose of a salt bridge is to keep both of the half cells electrically neutral. If you don't have that salt bridge, current's not going to flow. And then it produces energy. You have a positive cell potential. So it produces a voltage. Electrolytic cells are unfavorable reactions. They do not happen on their own. And so since they don't happen on their own, some sort of power source is needed. You have to run electricity through it for it to work. The anode and the cathode are in the same chamber, so they're in the same container. You don't need a salt bridge because everything is in one container, and it uses energy. It has a negative voltage, negative cell potential. Both types of cells, you have oxidation at the anode, reduction at the cathode. You have your cations in the salt bridge flowing to the cathode, your anions flowing to the anode. Remember, your electrons flow from A to C, so they flow from the anode to the cathode. And then your anode decreases in mass because you have oxidation occurring. Your cathode increases in mass because that's where you have reduction occurring. So that took what we did over like 4 days and put it into one slide. Here's just a picture of both. So your galvanic, you have two separate containers with the salt bridge, the wire, and the voltmeter. An electrolytic cell, you have everything in the same container. They're connected with a battery. So an electrolytic cell needs a battery to work because it has a negative cell potential. So topic 8 looks at cell potential and free energy. So with cell potential, to calculate cell potential, we always do reduction plus oxidation. So we have to figure out what is being reduced, what is being oxidized. Remember, a voltaic cell always has a positive cell potential. That means it's thermodynamically favored. Electrolytic cells always have a negative cell potential. So it's never thermodynamically favored. When we're looking at cell potential, we have to identify the oxidation and reduction half reactions. We are always, always, always given reduction half reactions. They always give us reduction potentials. The more positive the reduction potential, the more likely that substance is to be reduced. So even though these are both negative, negative 0.45 is more positive. It's closer to 0. So that means that Fe2 plus will be the one that is reduced, which means the second one I need to flip. And when I flip it, I flip the sign. The only thing you ever do to cell potential is flip the sign and add them together. You never multiply. Then if we want to calculate delta G, this is also on your equation sheet. Delta G equals negative N times F times E naught. N is the number of electrons that are transferred. So when I flip this second reaction, remember to make the overall reaction, we have to make our electrons equal. Well, if this one's 2 and this one's 3, more than likely, what will I make them both equal? 6. So N would be 6. F is Faraday's constant, that's on your equation sheet, and E naught of cell is your cell potential. Topic 9, what happens if we're trying to figure out cell potential under non-standard conditions? So in a real system, it's going to be under non-standard conditions, and cell potential will vary. Cell potential is the driving force toward equilibrium. Farther we are from equilibrium, the greater the cell potential. Remember, equilibrium is where batteries go to die. Cell potential is 0 at equilibrium. When we're thinking about non-standard conditions, we have to look at Q. Products over reactants do not include solids. When we look at Q, the greater your value of Q, the lower the cell potential. Because the higher your value of Q, the closer you are to the equilibrium constant. So the higher your value of Q, the closer to the equilibrium constant you are, and the closer to equilibrium you are. Closer to equilibrium, the lower the cell potential. If Q is really small, that means you're further from the equilibrium constant. You're further from equilibrium, so you're going to have a greater cell potential. We do not use Le Chatelier's principle when we're talking about non-standard cells, because these cells are not at equilibrium. If they're at equilibrium, voltage would be 0. And then remember, changing the mass of a solid does not affect cell potential because there's no solid in Q. There's no solid in Q, so changing Q or changing a solid isn't going to matter. What matters is changing from non-standard. Remember, standard is 1 molar. So if we're changing from 1 molar, we're going to change Q. And the last thing is electrolysis and Faraday's law. This is when we use Stoic. So this is when we use current. That was coulombs per second. And we either started typically with grams or with time, and we converted to one or the other. So we could find time, we could find mass, we could figure out electrons. And so this is when we just use dimensional analysis. Current is coulombs per second that allowed us to go between charge and time. So Faraday's constant is on your equation sheet, so you can always use that. You always have that. That's coulombs per mole of electrons, and your electrons are determined from your half reaction. So it says you have CuNO3 that's Cu2 plus, means you have 2 electrons. And so this is just using stoichiometry.